4,000 years is the time required for a single discarded tire to naturally decompose. This extreme longevity once made rubber wheels one of the most notorious forms of waste, so toxic that landfills rejected them almost everywhere. At first glance, it seems impossible to utilize such a stubborn material safely. Today, however, that very same waste is being actively sought after by engineers. Why has this hazardous material suddenly turned into the black gold of modern road construction? The answer lies in the mechanical properties of the rubber itself. Processing unlocks an entirely new life cycle for a material that was once considered completely useless. The transformation begins with industrial crushers, where giant blades rotate ceaselessly. One can notice how the tough rubber splits apart under pressure. Precision screening processes take over, sorting the debris by size. It is visible how the raw material turns into ultra-fine rubber granules. But this is just the beginning. The process is only gaining momentum as the granules prepare for fusion. These particles mix with hot bitumen, melting into a unified mass. This combination creates a road surface with exceptional durability, exceeding standard asphalt. The material is now ready to serve its new purpose on the highway. 1.5 billion tires are discarded by the world every single year. Why does such a colossal volume of waste pose a critical threat? To the naked eye, the storage sites look like static landfills. But without processing, the rubber barely breaks down, continuously leaching toxic chemicals into the soil. One can notice how these dumps resemble dark oceans stretching all the way to the horizon. Consequently, vast territories in the United States, Europe, and the Middle East turn into some of the most severe pollution hotspots on the planet. At first glance, the situation seems dire, but in reality, this waste triggered an unexpected turning point. Rubberized asphalt has evolved into a multi-billion-dollar industry. But this is just the beginning. Just 1 kilometer of road surface can reuse up to 10,000 old tires. It is visible how the new surface resists cracking and reduces traffic noise by around 6 decibels. From a symbol of pollution, the tire is now emerging as a promising, sustainable construction material of the 21st century. Thousands of vehicle tires reach the absolute limit of their service life every single day within the steady rhythm of modern cities. Why do these worn-out components pose such a severe long-term risk to the ecosystem? To the naked eye, a tire pile appears to be nothing more than a stack of static, harmless rubber rings. But in the natural environment, a single tire can persist for decades with little to no decomposition, slowly leaching organic compounds and heavy metals into the soil and groundwater. They accumulate at roadside garages, maintenance stations, scrap collection yards, and large-scale tire replacement centers after exceeding safe limits for tread wear and elasticity. Furthermore, when stored outdoors, they trap rainwater and become breeding grounds for disease-carrying insects, creating a biological hazard alongside the chemical one. In many countries, a worn-out tire is worth only a few cents when sold as scrap. Yet, from the perspective of the recycling industry, it represents a true form of urban ore. Inside every tire lies a complex blend of natural rubber, synthetic rubber, reinforcing steel, textile fibers, and chemical additives. All these materials can be recovered and reused with significant economic value when processed correctly. The collection process is typically organized along fixed routes to ensure efficiency. Specialized trucks, equipped with high-load platforms and secure fastening systems, gather tires from multiple locations to reach optimal transport volumes. This approach not only reduces logistical costs, but also prevents tires from being exposed to the elements. But this is just the beginning of the transformation. The recycling process begins with handling the steel reinforcement embedded inside the tire. This component allows the tire to lock firmly onto the wheel rim when traveling at high speeds, ensuring safety on the road. However, in a recycling line, that same steel ring becomes the biggest obstacle. If it is not removed first, it can chip cutting blades, snap drive shafts, and bring the entire shredding system to a halt. Workers feed the tire into a specialized bead removal machine at the first stage of the mechanical line. Inside the chamber, a hydraulic hook system capable of generating enormous pulling force digs deep into the tire bead. One can notice how the machine uses brute mechanical strength to extract the entire steel core in just a few dozen seconds. The force is so intense that even the thick rubber body of the tire is violently twisted and deformed during the process. On average, each heavy-duty truck tire yields around 2 kilograms of high-quality carbon steel. Once separated, these steel wires are collected manually by workers and compressed into compact bundles. From here, the metal is transported directly to metallurgical plants where it begins a completely new life cycle. Meanwhile, the remaining tire carcass is now far more flexible and ready to enter the next stage of coarse shredding. Before mechanical processing begins, the tires pass through a high-pressure washing system that removes mud, oil residue, and embedded gravel from the surface. At first glance, this seems like a minor sanitary step, but in reality, it plays a decisive role in maintaining the stability and service life of the entire downstream production line. This protects the cutting blades and crushing shafts from premature wear caused by abrasive debris. Whole tires are fed into high-torque cutting machines during the primary shredding stage. Slowly rotating alloy steel blades slice them into coarse fragments measuring several inches across. This low-speed cutting method minimizes heat generation, preventing the rubber from softening or sticking to the blades, while shaping the material into a form suitable for further processing. The shredded pieces then move into secondary grinding, where their size is reduced even further. It gets more complex further on. The internal steel reinforcement is mechanically fractured and gradually separated from the rubber during this phase. High-strength magnetic systems recover the steel directly from the material flow, turning this reinforcement into a valuable stream of recyclable metal. The final output is crumb rubber with tightly controlled particle size, stable enough to move on to classification or reuse. At this stage, the tire has completely lost its original form and becomes a raw material ready for new applications in construction, transportation, and industrial manufacturing. At the end of the production line, all material passes through a classification screening system. Particles that meet the required size move forward, while larger pieces are routed back to the grinder for further processing. Among these outputs, the fraction ranging from 0.5 to 2 millimeters is especially critical. This is the exact rubber size used to produce rubberized asphalt, which opens the path to a sustainable infrastructure solution. 260 degrees Fahrenheit is the maximum temperature hot air reaches inside the drying drums to prepare crumb rubber for asphalt production. After the initial crushing and screening stages, the material extracted from waste tires still retains residual moisture and fine dust deep within its structure. These microscopic contaminants interfere with the chemical interaction between rubber and hot bitumen, preventing the mixture from achieving the necessary stability. Therefore, before blending begins, the granules must undergo a dedicated heating stage to reach an ideal condition. But this is just the beginning. Why is such intensive thermal processing required for already crushed rubber? It would seem that mechanical cleaning is sufficient to prepare the raw material. However, moisture trapped in the pores creates steam pockets upon contact with hot asphalt, destroying the pavement's internal bond. Granules are fed into a large steel cylinder set at a slight incline, which keeps the mass in constant rotation to ensure even exposure. One can notice how the material tumbles inside the drum as burners fueled by natural gas or fuel oil pump hot air into the chamber. The temperature is strictly regulated between 200 and 260 degrees Fahrenheit to drive off moisture without burning the particles. Sensors monitor the airflow to ensure the rubber surface becomes chemically active and ready for bonding. It gets more complex further on. Many facilities rely on indirect heating methods to strictly isolate the flammable material from open flames. This method preserves the internal polymer structure, allowing the particle to retain its elasticity during the harsh processing that follows. The dried rubber is then ready to absorb bitumen effectively, creating a binder that is far more resistant to cracking than standard asphalt. Immediately after drying, the material enters the blending stage, where the true value of recycling is realized. Bitumen is heated separately in storage tanks until it reaches a liquid state between 320 and 375 degrees Fahrenheit. This thermal range ensures proper flow without degrading the chemical structure of the binder. Crumb rubber is introduced into the mixing chamber in carefully controlled doses, typically ranging from 10 to 20% of the total mass. At first glance, this appears to be a simple mixing operation, but in reality, it is a complex chemical modification process lasting 30 to 60 minutes. Heat-resistant paddles generate a continuous vortex, forcing the components into intense contact. It is visible how the rubber particles do not merely disperse, but actually swell within the mixture. They absorb the lighter oils from the bitumen, significantly increasing the viscosity and elasticity of the final product. The resulting material becomes capable of withstanding heavy traffic loads and constant temperature fluctuations. Automated systems monitor residence time and viscosity to prevent clumping or phase separation inside the tank. Some plants introduce stabilizing additives to ensure the mixture remains uniform during storage or long transport. By the end of this cycle, the rubberized asphalt reaches a homogeneous state and is discharged into dump trucks. The beds of these vehicles are preheated to prevent the material from sticking or cooling prematurely. And this is not the limit. One can notice the steam rising as the mixture is loaded at temperatures between 270 and 300 degrees Fahrenheit. This heat allows the asphalt to retain its self-leveling properties during transport to the construction site. Upon arrival, the driver releases the hot mass into the hopper of the asphalt paver. Internal augers distribute the material evenly across the full width of the lane. The screed plate at the rear lays down the layer at a thickness of 1.5 to 3 inches, depending on the specific road design. Immediately after placement, the compaction phase begins. Steel vibratory rollers provide the initial finish, while pneumatic tire rollers seal the internal air voids. The entire sequence is calculated to finish before the mixture cools below 180 degrees Fahrenheit. Below this threshold, the binder loses its optimal capability to bond the aggregate, compromising the road's integrity. Compaction machinery moves continuously to ensure the density meets engineering standards. Thus, the recycled tires officially become an integral part of the road infrastructure, ready to serve for years. Just a few hours is strictly all the time needed for the recycled tire asphalt to harden completely before traffic returns. Roads that once seemed to have reached the absolute end of their service life receive a new beginning here, saving thousands of tons of raw materials and significantly reducing carbon emissions. However, under the constant stress of heavy traffic loads and environmental exposure, even rubberized asphalt gradually deteriorates with cracks and surface rutting beginning to appear. But this is just the beginning. What is remarkable is that asphalt can be recycled repeatedly, almost without limit, while still retaining its technical value. Why is this material kept in circulation instead of being discarded? The cycle might seem redundant at first glance, but in reality, turning aging roads into raw material for the next generation of pavement ensures sustainability. Even when originally produced from recycled tires, the mixture continues to circulate within the infrastructure system. Wheel loaders or mini excavators move in to begin the removal and collection phase once the asphalt slabs have been separated. Operators carefully lower the bucket to the very edge of each cracked slab, then lift gently to pry the entire section up without damaging the base layer underneath. Smaller pieces are gathered into clusters before being loaded onto trucks, while larger slabs are broken apart using the bucket or steel bars for easier handling. One can notice how workers assist with shovels and pry bars to loosen the edges when the asphalt remains tightly bonded, allowing the machinery to work faster. It gets more complex further on. Each bucket can hold between 200 and 400 pounds of asphalt debris at a time. Within just a few hours, dozens of tons of material are cleared from the road surface by the heavy machinery. Trucks are weighed, assigned batch numbers, and logged with their excavation zone before leaving the site, ensuring full traceability of the reclaimed asphalt pavement for future quality control. Once the surface has been completely stripped, the crew performs mechanical sweeping and base leveling to prepare for fine milling in the next stages of recycling. Though it may seem like a straightforward task, this phase determines the precision and efficiency of the entire recycling process. Every slab of asphalt is separated, collected, and made ready for its journey of rebirth. After the old pavement is removed and transported from the site, all the material is sent to a recycling plant. Here, every ton of used asphalt begins a process of separation, cleaning, and size standardization, preparing it for the next stage of mixing. Trucks unload the wrap into a feed hopper, where the material moves along a vibrating feeder that separates debris, soil, scrap metal, and concrete fragments collected during milling. One can notice how large metal pieces are extracted by an electromagnet while the remaining material enters the impact crusher. And this is not the limit. Inside the crushing chamber, high-speed hammers rotating at 1,000 or 800 revolutions per minute strike the asphalt against fixed impact bars. The mechanism continuously breaks the chunks apart, separating the aged bitumen from the stone aggregates with intense force. Adjustable impact wings allow operators to fine-tune the gap between the rotor and the bars to control the output size. The resulting particles typically range from 0.5 to 2 inches, depending on regional or manufacturer mix specifications. Everything only gets more complicated. After crushing, the material passes through a multi-deck vibrating screen for classification. Oversized particles are recirculated back to the crusher, while properly sized aggregates are divided into groups: coarse wrap, fine wrap, and mineral dust fines. Some plants also include an air separator to remove light dust, ensuring cleaner aggregates and improving binder adhesion during remixing. In modern facilities, the entire process is automated and monitored through sensors that track vibration, temperature, and material flow. This guarantees consistent quality of the processed wrap. On average, a single plant can handle between 100 and 300 tons of wrap per hour, recovering up to 30 or 40% of material ready for direct reuse in new asphalt mixes. This is one of the most critical stages in asphalt recycling, where old pavement is reborn into a clean, uniform resource ready to enter the drying and heating phase of the loop. Zero remains. This is the defining characteristic of the closed-loop process. Why integrate millions of discarded tires into fresh asphalt mixtures? Superficially, it appears to be a simple method of hiding trash within the roadbed, but this specific modification actually transforms a massive ecological burden into a functional resource for strengthening highway infrastructure. Rubberized asphalt represents far more than a simple technical upgrade. One can notice how the finished surface absorbs vibration and sound. The dark, modified material creates a drive that is significantly smoother than traditional concrete pavement, Tires once considered worthless now reinforce the binding matrix against cracking. But the utility does not end there. At first glance, worn-out rubber looks like mere waste, but in reality, it dictates the durability of future transport networks. As these technologies spread, they reshape the engineering approach to material life cycles. Value is determined not by the visual state of the element, but by the decision to repurpose the structure. The cycle closes here, leaving a resilient path for future transit.